Hello, everybody. So let's talk about chemical reactions and specifically talk about reactions that pertain to solubility and solutions. So with regards to solutions, the first thing you want to know is, first of all, what exactly is a solution? So a solution in chemistry is defined as essentially a solvent and a solute, and the solute is what gets dissolved in the solvent, and as a result, you get a solution. Here's an example, a pictorial example. You can see these are small particles being dissolved in the solvent, which would make these particles the solute. Solvent is what dissolves the solute. The other important notion to keep in mind is that every time you dissolve a solute into a solvent, you have to be following this notion of like dissolving like. So really what this means is that if your solute is to dissolve in your solvent, they have to be alike. Now, what does alike mean, or how do we group these compounds? Well, for the purposes of this course, let's focus or classify these solutions or compounds into two groups. The first group, as you can see on the left, let's just call them hydrophilic or lipophobic. And on the right, let's call them hydrophobic or lipophilic. So philis means you like something. So here you like hydro or you like water. Phobia means you're scared of something or you don't like it. So here you don't like lipids or fats. So essentially what this means is that if you like water, you're going to be disliking fat. By the same token, on the right, if you have phobia or you're afraid of water, if you don't like water, then you must like or philis lipo or lipids. So the examples that pertain to the first group on the left include things like polar compounds, such as, glucose, alcohols, and then you also have ionic compounds in this group. And again, those include things like, sodium chloride, magnesium hydroxide. Let's call polar compounds in this class 2. Let's call ionic compounds class 3. And then class 1 compounds, those would be all hydrophobic or lipophilic. And essentially, those are all of our non-polar compounds. So the next question is to ask, well, how does a solute dissolve in a solution? So the answer is, well, there's a process. When you're dissolving something, it doesn't happen quickly, all right? You still have to do some work. There's a process behind dissolving anything into anything. So in this case, the process is what we call solubility. So solubility is the process of dissolving solutes into solvent. Now, this becomes a thermodynamics thing. So essentially, you're thinking about energy exchange. Really, when we look at solubility as a process, one way to look at it is to say, well, solubility is really equal to the total number of bonds being broken, breaking bonds between solute particles and between solvent particles. And then after that, you want to be forming bonds between solute and solvent, which I think conceptually makes sense, right? When you're trying to dissolve a solute into a solvent, first you need to break the bonds between the solutes and the bonds between solvents, and then you can form bonds between the solutes and the solvents. Now, what happens is that there's an energy exchange happening here. There's an energy exchange happening here, and it's really the net energy exchange, okay, of the two processes that determines solubility. If the net energy exchange of the whole thing is negative or less than 0, then you are soluble. And in fact, the more negative the number or the larger the negative number, right? So if you go from -1 to -100, this is somewhat okay, but -100 is very good because it's a larger negative number. If, on the other hand, the exchange in energy is a positive number or more than 0, then it becomes either very hard to dissolve or impossible to dissolve. We'll talk about energy in more details in a second, but you have to understand first that when you are breaking bonds or any type of bond, you always need a positive energy exchange in that you need energy input. Okay, so when you want to break any bonds, you have to use energy. Just like when you're trying to break something hard, you need to invest energy, right? So that means you have a positive number or input of energy. Forming bonds in chemistry always is a negative thing, always has a negative number, and it always releases energy. So you always release energy when you form bonds. You always need energy when you're trying to break bonds. At that point, you can see this becomes a mathematical thing, right? So imagine if here I have, let's say, +20 and here I have -25, then of course my net change would be -5. I am negative. I'm going to be dissolving. If, however, I have a 20 joules or kilojoules per mole energy input here and a -5 kilojoules output here, then my net exchange would be a positive number, and so then I'm not going to really dissolve. Or if I want to dissolve, I have to increase this number on the right, maybe take it from -5 to -50, and I will dissolve. So really, at a very molecular level, it becomes a thermodynamic thing for things to dissolve, and that's what I'm trying to show you guys here. Essentially, that's just a summary of what I mentioned. So if you need to break bonds, you need energy input. That number is always positive, and if you're forming bonds, that number is always negative. The net exchange determines solubility. If you're negative in total, you will dissolve. If you're positive, you will not dissolve. In grade 12, you folks learn about delta H. This is also another summary. So if you're net exchange of energy is negative, then you're going to get solubility. In fact, the larger the negative number, the more solubility you will have. And if your net exchange is positive, it will not dissolve. So that's the first thing I wanted to cover. The second thing I wanted to cover is to really zero in on different types of solutes. So if you remember up here, I mentioned that let's classify this group in class 1, classify this group in class 2, and classify this group in class 3. Notice that both classes 2 and 3 are considered hydrophilic or lipophobic. So when you zero in on these classes of solutes, and again, the presupposition is that you're trying to dissolve these guys in water, right? So let's just keep water as our solvent. Then you really are facing 3 different microprocesses, right? So the process of making a solution here that I discussed was, again, one way of looking at things. So that would be looking at things from a thermodynamic perspective. Here, we're looking at things from a more of a molecular interaction perspective, okay? So no energy, but rather how particles or species interact. When you look at class 1 compounds, we know that those are lipophilic or nonpolar compounds, and those guys, they simply don't dissolve. Although if you shake and agitate test tube here, for example, you may get these small particles of oil droplets trying to dissolve, but then even then they kind of bounce back up and they join their other folks up here. That sort of separation of these bulk fat or oil piece into these smaller oil particles is called agitation. The best you can get in class 1 solute case is agitation. You don't get any dissolution. You don't get a solution of water and fat. That's impossible. When you look at class 2, you get agitation, of course, right? You still have that step. You know, what does that mean? So if you think about a piece of cube sugar, and this would be water down here, you guys have seen this before, that, you know, the cube sugar gets broken into smaller pieces. Again, that's the same thing as up here, guys, is taking something bulky, break into smaller pieces. Well, we still have agitation, but something extra happens because these guys are polar. And that extra step is called dissolution. And that is the part that essentially, in our eyes, we refer to as dissolving. So when we say sugar dissolved in water, really, we're talking about this step, not really this, right? So what does that mean? So if you actually look at this sort of area and zero in on it and blow it up, right? So zoom in it, you will see this sort of picture where these would be your glucose particles, and I've drawn the molecule here. And then you would have the water molecules around. And if you remember our lessons on intermolecular forces, you would have hydrogen bonds, for example, formed sometimes, and other polar interactions, and then you would dissolve, right? Again, that's because like dissolves like, and you know, we know glucose is polar, you know water is polar, perfect. You get dissolution and it dissolves. Now there are limitations to this. You can't keep adding sugar into water. If you have so much volume of water, eventually you will precipitate, but we'll talk about those notions in the future. When we look at class 3 compounds, such as ionic compounds, then the story is again a bit different. So remember, the first step always remains, right? So you still have agitation, but the second step is not necessarily dissolution. There is an intermediary step called ionization or dissociation, which we did not see in glucose or class 2 solutes. When we dissolved glucose into water, glucose remained glucose. It didn't break into 2 particles or something, right? It didn't ionize. Here, when you put salt into water, you have this step called dissociation or ionization. Okay, so what does that mean? So again, think of a big piece of salt or a lot of salt into water. If you look zero in on it, you have agitation, you become smaller pieces. Let's just say this is piece after agitation, small piece of salt crystal. The first thing that happens is dissociation, where remember here, this is solid or NaClS, solid salt. But then as soon as it faces water, sodium and chloride ions separate. So separation of ions, right? So here they're not separated. They're in a crystal lattice structure. But once they separate into positive, negative charges, we call that step dissociation or ionization. And then you get a bunch of sodium cations here, a bunch of chloride anions down here. Of course, we have water floating around. And guess what? Water is polar. And you can see here, if you zoom in, you guys know from previous classes, oxygen would be partially negative. The hydrogen atoms would be partially positive. And the negative area of water will interact with the positively charged sodium cations, and then by the same token, partially positively charged hydrogens of water will interact with chloride anions of salt, and that part is the dissolution step. That's the last step, and then you get salt dissolved in water. Okay, so dissolution of or dissolving salt in water or ionic compounds has 3 steps for class 3. If you're class 2, you have 2 steps. You're a 2-step process. You have agitation, dissolution. If you're class 1, you only have 1. So you can use this mnemonic: class 1, 1 step; class 2, 2 steps, class 3, 3 steps. That's the lesson I wanted to talk about. And dissociation is a broader term, which doesn't just apply to salts dissolving in water, as although that's what we call it up here. Dissociation in a broader term means breaking your ionic compound into its ionic species. Okay, so remember, ionic compounds in their solid form, when there's no water around, that on average, there are some exceptions. They tend to be in crystal lattice structure. They're together. They're ionized, but they're stuck together. They're not separate. So think of Na plus and Cl minus still here, except they're literally touching each other, that they're just next to each other. But if you separate them completely, right? So put one all the way up here and the other one all the way down here. Now that's called dissociation. And dissociation is very common for these ionic compounds to happen in water. And depending on how many ionic particles you get after you dissociate, we will count the number of those ions, and that would give us a number called the Van Hoff factor. The Van Hoff factor, or I, is simply a number that represents the number of ions produced after you dissociate an ionic compound for every mole of the compound. So if you have 1 mole of salt, you get 2 moles on the right. Why? Because you get 1 mole of sodium and 1 mole of chloride. The Van Hoff factor is 2. You look at ammonium chloride, you also get 2 species. You get ammonium cation and chloride anion. But when you have something like ammonium sulfate, because you get 2 moles of ammonium and 1 mole of sulfate, then in total you get 2 plus 1, which is 3 moles on the right. And so in that case, your Van Hoff factor is 3. So how do you get these numbers? How can you figure them out? Well, you need to know how to write reactions of ionic compounds, and you need to know what type of ions they form, and then you balance them. After you balance the reaction, you can find that I. And as you get at this, guys, don't worry, you can actually look at a compound without breaking into pieces and tell me what the I is. For now, because you just got introduced into this, write the salt in solid form, figure out what ions it forms, balance the reaction, add the number of moles that you get, or the molar ratios you get for each ion. The total number will give you the Van Hoff factor. If you have a compound such as glucose, that when you put in water, you get glucose aqueous, of course, but there is no breakage, there's no separation of glucose into 2 subparticles, then your Van Hoff factor is simply 1. The Van Hoff factor doesn't only belong to or apply to ionic compounds. It can technically apply to any solute, any species for that matter, that faces water. And so, we usually use Van Hoff factor when we have water as a solvent. So if you put anything in water, think of anything you add to water, if it doesn't break into pieces, and again, I'm not talking about agitation here, guys, right? Of course, if you put a cube sugar in water, it breaks into pieces. It has nothing to do with Van Hoff. So if you take a single functional unit of your solute, and then if it doesn't break into pieces, if you still have 1 piece after it dissolves, then that determines the Van Hoff factor. So for glucose, after it dissolves, you still have 1 single glucose. The Van Hoff factor is 1. So that's the end of the lesson. Talk to you guys soon.